ट्राई किया, कोन का मोमेंट ऑफ इनर्शिया आया, हॉलो कोन का क्या आया, एम आर स्क्वायर बाई टू, हॉलो का एम आर स्क्वायर बाई टू आएगा, नहीं वो सॉलिड का आएगा, सॉलिड का 3/10 आएगा। हाँ ठीक है। सो डिड ऑल ऑफ यू अटेम्प्ट, गॉट इट, नहीं, हाँ तो सही तो आया, दैट्स करेक्ट, फॉर हॉलो दैट्स करेक्ट, फॉर सॉलिड यू विल गेट 3/10 mr square. Alright, so let's proceed. So now we have all the things that we require to understand rotational dynamics. Okay, so we are comfortable with the torque, we are comfortable with moment of inertia. Okay, so now we'll dive into rotational dynamics. Okay, so whenever we are dealing with rotational dynamics, alright, we have to first understand what kind of rotational motion is this. Okay, so broadly we can divide rotational motion into two parts. So one is pure rotation. Have we discussed what is pure rotation? Pure rotation is when the axis does not move. Okay, so what does it mean? It means that the axis of rotation does not move. Alright, and this could be rotation with translation. Okay, so rotation and translation, obviously you understand that it would be rotating about its axis, but the axis is also moving. Alright, this is known as rotation with translation. Again, when we are dealing with rotation with translation, we could have two kinds of motion. One is known as pure rolling. Okay, we'll talk about it, what is pure rolling. There's a difference between pure rotation and pure rolling. Okay, don't confuse these two terms. So when there is rotation with translation, it could be either pure rolling or it could be everything else. Okay, not pure rolling, I can write that. Okay, so that we'll deal with later. So dealing with this is very simple. Dealing with this is also simple. This is the part where you'll have most of the problems. Okay, that will be the difficult part, जिसको कहते हैं, when it is rotation with translation, but it is also not pure rolling. Alright, so any question we are trying to deal with, first we have to be certain what kind of rotation is it. Okay, so there are different methods to follow for each of these three things. Okay, we are going to discuss that one by one, but we'll start with, of course, we'll start with pure rotation. Okay. So what have we seen? Have you seen this? For a translation of a body, have you seen this? The summation of all the forces will be equal to mass into acceleration. I can put. So we already know, we have done laws of motion. We already know how to deal with forces and acceleration, and deal with and how to write the dynamical equation, or how to write the force equation. We know that already. Okay. So what has been added here is, since the object is rotating, it may have an angular acceleration. Alright, so summation of all the torque will be equal to I into alpha. These are the only two things we need to deal with rotational dynamics when it is just pure rotation. Alright, these two things. Is that clear? Any problem? Okay, so let's start with a very simple example. Suppose you have AC क्यों नहीं चल रहा है यार? Obviously. So let's say this is 1 meter. This is at the center. This is, let's say, 2 kg, and this is, let's say, 3 kg. Okay, and the rod has a mass, let's say, 1 kg. Okay, these are small masses. This 2 kg and 3 kg are small masses. Okay, so initially the rod is horizontal. Initially this rod is horizontal, and then we leave it. Okay, so the question is, find the initial angular acceleration. Okay, the question is, find the initial angular acceleration. Okay, so how do we go about finding the angular acceleration? What do we need to find the angular acceleration? We need the torque. Okay, so first of all, let's decide what kind of rotational motion is this. नहीं, clockwise तो है ही, but what kind of rotation is this? It is pure rotation because this axis about which it is going to rotate, this rod about the axis about which it is going to rotate, that's stationary. Okay, so this is simply pure rotation. So dealing with pure rotation is extremely simple. Find the torque equals I into alpha. All right. So what will be the torque? So this would be half meter, and this would be half meter. Okay. So 3 kg का torque नीचे कितना लग force होगा 3g. And then what will be the clockwise torque? The clockwise torque would be 3g into half. That's the clockwise torque. Okay. Then इसका क्या होगा? The force is 2g and the torque is 2g into half, but this torque is anti-clockwise. So we'll have to write minus 2g into half. Is this the net torque? Alright, this is the net torque. Anything else? The weight of the rod is going to go from the center. Will that make any difference? No. So this is the net torque. So this net torque has to be equal to what? It has to be equal to I times alpha. Okay. So what is my system? ठीक है. Okay. So तुम्हारे उसके लिए hang on. ताकि तुमको confusion नहीं हो, I should make it like this. What is this? 2 kg? 3 kg. ठीक है. So what does this mean? This is very close to the end of the rod. Very close to the end of the rod, and these masses are small. Okay. So what is my system? What is the system on which I'm calculating the torque? The rod, and yes, just the rod. Actually, the net what we are calculating is about just the rod. ठीक है. The torque we have calculated is on what? Is on the rod. ठीक है. The torque we have calculated is no. The torque we have calculated is नहीं, tension नहीं. The torque we have calculated is the rod plus the two masses. ये लिए ना. We have took this. This is 3g. This is 2g. Okay. So the torque we have calculated is on the entire system. What is that system? The rod plus the two masses. Okay. So this is the total torque. This should be equal to I into alpha. So what will be I? सबसे पहले m, and then you'll have L square मतलब 1 square divided by 12. That is the moment of inertia of, क्या आएगा? अरे नहीं, this is first of all, this is the moment of inertia of the rod. This is the moment of inertia of the rod, just the rod. Okay, what else is there in my system? The masses. Then we have to take इसका moment of inertia. This I'm saying is a small mass, so we can treat it as a point mass. So इसका moment of inertia कितना हो जाएगा? 3 into half square, correct? And then इसका moment of inertia कितना हो जाएगा? 2 into half square. So this is the total moment of inertia. This multiplied by alpha will give me my equation. Is that correct? Any problem? Equation of torque, calculation of torque and calculation of moment of inertia is clear to everyone? Alright, can I rub this off? Okay, so let's go to a very standard problem, and you have been solving this for a very long time. Okay, but the difference here is, that this pulley right now is not massless. We have always been dealing with pulleys which are massless. Okay, it is still frictionless. उसमें कोई change नहीं आया है. नहीं, now it cannot be frictionless. उसके बारे में बाद में बात करेंगे. That it has to be with friction. Otherwise ये roll ही नहीं करेगा. Anyway, so this pulley now has a mass. Okay, so what is the mass? Mass is something. Let's call the mass m. It has a moment of inertia of I, and it has a radius of r. Okay, these are the properties of the pulley. Okay, mass m, moment of inertia I, and radius r. Okay. Now the system is set. The system is left from rest. Okay, the system is released from rest. So we have to calculate the acceleration of the masses and the angular acceleration of the pulley. ठीक है, the acceleration of the masses and the angular acceleration of the pulley. Okay, so how you're going to do it is exactly the way we have been doing it. Okay, first of all what you will do is draw the free body diagram. So m2g, m1g, t1, नहीं t2 कह लेते हैं इसको. So this is t2, this is t2, this is t1, this is t1. Now can you tell me why have I marked different tensions on the string? Because the pulley now has mass. तो उससे क्या होगा? So what? Right. So if this mass is accelerating, it means this pulley has an angular acceleration. Alright, this pulley has an angular acceleration. If this pulley has an angular acceleration, then the net torque on the pulley should be not equal to 0. Okay, so if I assume the tensions on both the sides to be equal, the net torque on the pulley would be 0. Is that correct? Okay, so it won't have any angular acceleration. But that's not the case. If this is accelerating, this has to have angular acceleration. For that, नहीं frictionless नहीं है. Frictionless होगा तो ये rotate ही नहीं करेगा. ठीक है, उसके बारे में बाद में बात करेंगे. Don't worry about that right now. Okay. So the tension on both the sides would be different. Okay. Okay. Suppose if I have a pulley which has a mass, but it does not have an angular acceleration, then will the tension be same on both sides or different on both sides? Same on both sides. Okay. So just because the pulley has mass does not mean that the tension would be different on two sides. Okay. For example, let's say mass m, mass m. So this has I m prime small r. In this case, the tension on both sides would be the same or would be different? Would be the same. Why? Because the pulley does not have an angular acceleration. If the pulley does not have an angular acceleration, the net torque is 0. So for that, the tension on both the sides should be same. Is that clear? Okay. So just because it has mass does not mean it will have different tensions. If it is angularly accelerating, that is when it is going to have different tensions. Is that clear to everyone? That is the reason why we mark two different tensions there. Any problem? Okay. So our first job is to find the constraint equation. We have always been talking about the constraint equation. Okay. So this is simple. Constraint equations are still going to be valid. Why they're going to be valid? Because of rotation, there is no change in the constraint equation. Why? Because our constraint is that the length of the string is constant. Okay, so whether the pulley is rotating or not, it has mass or not, it does not matter to the string. Okay? So if this has an acceleration of a, this will have an acceleration of a upwards. We know that already. Is that correct? Okay. Now there is a third variable now, which is the pulley. So you have to assume an angular acceleration for the pulley. Okay, you have to assume an angular acceleration for the pulley. Now very logically tell me what should be the direction of angular acceleration. Okay, so this is going down, this is going down. So this is going to rotate clockwise. So I'm going to assume an angular acceleration of alpha. Is that correct? I'm going to assume an angular acceleration of alpha. Clear? Okay. So one of my equations, the first equation for this mass would be, and we have been writing this for a very long time, m2g minus t2 is equal to m2 into a. Straightforward. Okay. What is the equation for this one? This would be t1 minus m1g is equal to m1 into a. Alright. Any problem? Okay. Now we also need to write the torque equation for the pulley. Okay, so the torque equation for the pulley would be what? You have assumed alpha to be clockwise. So the torque which is clockwise, you will assume it to be positive. The clock which is anti-clockwise, you are going to assume it to be negative. Correct? So the clockwise torque is how much? T2 into R is the clockwise torque. So I'm going to write plus T2 into R. And the anti-clockwise, I'm going to write minus T1 into R. And this should be equal to what? This should be equal to I into alpha. ठीक है? हाँ उसी पे आ रहे हैं, exactly उसी पे आ रहे हैं. Okay, so how many variables do we have? We have T1, we have T2, we have A, and we have alpha. Okay, so from where would the fourth equation come? The force is acting as tangential force. String is a straight line, so it is always going to be a tangent to this pulley, correct? So yes, this tension is tangential to the pulley. What will be equal to alpha r? A is equal to alpha r. ठीक है, how did you get to A is equal to alpha r? What is the reason? You are correct. A is equal to alpha r will be a relationship between the acceleration and the angular acceleration. Now what is, from where did you get A is equal to alpha r? Circular motion. Elaborate. It is tangential force. ठीक है, फिर नहीं, टेंजेंशियल फोर्स का एक्सेलरेशन इज ए का क्या मतलब? इसका एक्सेलरेशन इज ए, हाँ इसका एक्सेलरेशन इज ए, सो व्हाट? ठीक है, नाउ थिंक, अंडरस्टैंड हाउ टू डू दिस. सो द पुली has an angular acceleration. If the pulley has an angular acceleration, can I say this point of the pulley will have certain acceleration, certain tangential acceleration? How much would that be? If the pulley has an acceleration, angular acceleration alpha, the rim would have a tangential acceleration of alpha r. You remember this? Tangential acceleration is equal to alpha r. याद है नहीं है? ठीक है, okay. So this point has a tangential acceleration of alpha r. What is the direction of that acceleration? That acceleration is downwards, obviously. ये horizontal है तो ये vertical होगा. Is that correct? Okay, so this point has an acceleration of alpha r. Okay, this point has an acceleration of a, right? So because this is connected by a one segment of the string, इसका मतलब क्या है? This length cannot change. That means the acceleration of this point and acceleration of this point has to be equal. इसको रट्टा नहीं मारने का. A is equal to alpha r रट्टा नहीं मारने का, क्योंकि जब हम लोग जाएंगे रोलिंग में और रोटेशन विद ट्रांसलेशन में जाएंगे तो फंस जाओगे. वहां पे A is equal to alpha r प्रॉब्ली नहीं होगा. Okay, understand how did we derive this? ठीक है, this point, the relationship between the acceleration of this point and this point. How do we get that? Use constraint relationship. वही किया है. Is that correct? So we will use constraint relationship to find the relationship between the acceleration and the angular acceleration. Is that correct? ठीक है, so this is A and this is alpha r. Both of them have to be equal. That is why we are going to write A is equal to alpha r. So this equation would be A is equal to alpha r. Is that correct? Any problem? ठीक है, so now we have everything to solve this equation. Okay, so we want acceleration, तो यहाँ acceleration, alpha को we can replace by what? Alpha को we can replace by a by r, and this r and this r we can bring it to this side. ठीक है, and then it's very simple, just add all the equations. ठीक है, if we add all the equations, t2 t2 t1 t1 गया, so we are left with m2 minus m1 into g divided by m1 plus m2 plus I by r square. Is that clear? ठीक है, so इसमें किसी को प्रॉब्लम नहीं होता है. इवन व्हेन वी गो टू रोटेशन विद ट्रांसलेशन, इसमें किसी को प्रॉब्लम नहीं होगा. द ओनली प्रॉब्लमैटिक थिंग देयर वुड बी दिस इज द क्रिटिकल थिंग. ठीक है, फाइंडिंग द रिलेशनशिप बिटवीन ए एंड अल्फा. In different situations, we'll have to use different methods. Okay, anyway, is this clear to everyone? Can I rub this off? Find the acceleration of the masses. Find the acceleration of the masses. Mm-hmm. T2R minus T1R, ना? तुम T2 उसको लिया है. देखो. हम्म. हम्म. Done? Alright. Nothing, no difference in this question. M2G. Let's assume this to be T2. So this will be T2. This will be T1. This would be T1. Then you have M1G. And then you have friction. That's it. Anything else? ठीक है. So इसका अगर we assume the acceleration to be a, then इसका acceleration would be a. Correct? And then iska, if we assume the angular acceleration to be alpha, then what will be the relationship between a and alpha? A equals to alpha r. Why? Because this point will have an acceleration of alpha r and this point has an acceleration a. Both have to be same. Correct? Okay. So what would be my equations? The first equation would be m2g minus t2 is equal to m2a. The fourth equation for this one would be t1 minus mu m1g. This is equal to mu1 into a. Is that correct? And the third equation would be, so this is alpha. Alpha we have assumed to be clockwise. So T2R would be positive and T1R would be negative. And this has to be equal to what? This has to be equal to I into alpha. We already know the relationship. A is equal to alpha R from here. So we can directly substitute alpha. What is that? Alpha is a by r. ठीक है, add, you'll get the answer. इस क्वेश्चन में थीटा नहीं दिया तो थीटा ले लो, करेक्ट, थीटा देना चाहिए. ठीक है, एनी प्रॉब्लम हियर? ओके, लुक एट दिस क्वेश्चन. द स्ट्रिंग इज रैप्ड अराउंड दिस पुली. ठीक है, द स्ट्रिंग इज रैप्ड अराउंड दिस पुली एंड रेस्ट ऑफ द थिंग्स यू नो. ठीक है, फाइंड द एक्सेलरेशन ऑफ द ब्लॉक. आई इसका वेरिएबल नहीं, स्ट्रिंग इज, सी स्ट्रिंग को तो हम लोग मासलेस ले रहे हैं ना, स्ट्रिंग इज मासलेस, सो उसका इफेक्ट नहीं पड़ेगा. एम जी साइन थीटा माइनस आई ए बाई आर. ये आई ए बाई आर क्या हुआ दोस्त? बट मेरे को समझ में नहीं आया दिस इक्वेशन. दिस इज डायमेंशनली रॉन्ग. पहले तो ये इक्वेशन, ये क्या है? आई ए बाई आर क्यों है यहाँ पे? तो एम जी साइन थीटा माइनस अल्फा, तो still mg sin theta is a force. I alpha would have the dimensions of torque. तो force minus torque करके क्या होगा? बट मेरे को समझ में नहीं आया, आया कहाँ से? और सोच. t sin theta into r क्यों? t किस पोजीशन पे है? तो सोच सोच, एक मिनट. करेक्ट. माइनस कैसे आएगा दोस्त? नहीं, सेकंड इक्वेशन देखा, मेरे को नहीं समझ में आया. एक बार चेक कर. करेक्ट. माइनस किधर से आया इसमें? क्या है आंसर? करेक्ट, उतना ही होगा. ठीक है, सिंपल है. देखो अगेन, सिर्फ देर इज एन एडिशन टू द टॉर्क इक्वेशन और उसके अलावा देर इज नथिंग एल्स. इट्स एग्जैक्टली लाइक लॉज ऑफ मोशन. ओके, हाउ डू वी डील विद दिस ब्लॉक if it is kept on an inclined plane? Okay, we say that the acceleration would obviously be along the inclined plane. If the acceleration is along the inclined plane, we are going to resolve forces along the inclined plane and perpendicular to the inclined plane. So this is mg sine theta, this is mg cos theta, normal to pata hi hai, and then tension over here and tension over here. That's it. Anything else? Okay, so what will be the force equation for this one? The force equation for this block would be what? Mg sine theta minus T is equal to M into A. Correct? Any problem? Okay, now this is the direction of acceleration. How is this pulley going to accelerate, or what will be the angular acceleration of the pulley? Anti-clockwise. Absolutely, it is going to be anti-clockwise. And can we find a relationship between alpha and A? Again, A is equal to alpha r. This point will have an acceleration alpha r, and this point has an acceleration A. So again, A is equal to alpha r. Done? Okay, then we will write the equation for this pulley. What will be the torque on the pulley? Do we need to resolve tension? No, tension will be tangential. Tension will be tangential. So tension into the radius is going to be the torque. Tension into radius is going to be the torque, and this should be equal to I into alpha. ठीक है, तो अल्फा के लिए what should we write? अल्फा के लिए we can write A by R. क्या तेरा साइन थीटा उधर किधर से आ गया? So this becomes R square, so A becomes mg sine theta divided by m plus I by R square. Clear? Any problem? Okay, try this one. So this string is wrapped around this pulley, and then वहां से यहाँ पे. माइनस टी टू आर, अच्छा टी वन, अच्छा टी वन आर टू मैंने, अच्छा ठीक है, एंड टी टू आर वन इज इक्वल टू, हाँ करेक्ट. माइनस एम तो नहीं आना चाहिए, प्लस एम आना चाहिए, चेक कर. क्या हुआ गया कृत, किधर अटका है तू? अल्फा वुड बी डिफरेंट और सेम, वेरी गुड क्वेश्चन. अल्फा वुड बी डिफरेंट और सेम. व्हाट विल बी सेम, पहले वो सोचते हैं. व्हाट विल बी सेम? टेंजेंशियल एक्सेलरेशन सेम होएगा कि नहीं होएगा? यस नो? व्हाई? सो दैट, देखो बहुत सिंपल सी बात है. लेट्स अज्यूम द एक्सेलरेशन, प्रॉब्लम एक ही जगह है, द रिलेशनशिप बिटवीन एक्सेलरेशन एंड एंगुलर एक्सेलरेशन, वही प्रॉब्लम, बाकी एवरीवन कैन राइट. ओके, नाउ दिस पॉइंट हैज एन एक्सेलरेशन अल्फा, सॉरी a. Now this point will have an acceleration or tangential acceleration of, let's assume इसका angular acceleration is alpha 2. Let's assume the angular acceleration is alpha 2. So for this point, what will be the tangential acceleration? Alpha to r2, direction obviously down. ठीक है, the direction would be down. ठीक है, so this point and this point, should they have the same acceleration or should they have different acceleration? They should have same acceleration. इसका मतलब है, what do I get? I get a is equal to alpha 2 into r2. Is that correct? ठीक है, okay, now let's go where? Let's go here. Let's go here. ठीक है, now tell me, this has an acceleration of a, so this point should have an acceleration of, and this point should have an acceleration of, correct? ठीक है, और अगर कंस्ट्रेंट से देखें तो these two points को अगर भूल भी जाओ तो just talk about this whole string. So this point should have the same acceleration as this one. Is that correct? Let's assume कि इसका angular acceleration is alpha 1. So what will be the tangential acceleration? The tangential acceleration would be alpha 2 r2. Sorry, alpha 1 r1. The tangential acceleration would be alpha 1 r1. Should that be same as a? Obviously that should be same as a. यानी कि this will also be equal to what? Alpha 1 into r1. Right? Problem solved. So all we need to do is write the equations. So इसको mg ले लेते हैं. Let's take it what? Let's take it t2, t2, t1, t1. ठीक है? What would be the equations? The first equation would be mg minus t2 should be equal to m into a. The second equation for this pulley would be equal to t2 into r2 minus t1 into r1. This should give me what? Sorry, t1 into r2. t1 but the radius is r2. ठीक है, so t1 into r2, this should give me I2 into alpha 2. This should give me I2 into alpha 2. What is alpha 2? A by r2. Sorted. Then for this I am going to write the torque would be t1 into r1. The torque would be t1 into r1, and this should be equal to I1 into alpha 1. And what is alpha 1? Alpha 1 is A by r1. ठीक है, add all the three equations. इस r2 को इधर ले जाओ, इस r1 को इधर ले जाओ, add all the equations, you will get A is equal to m g divided by m plus I1 by R1 square plus I2 by R2 square. Clear? Any problem? ठीक है. Now can you solve this orally? अब इतना practice कर लिया यार. Now can you solve this? There is no friction. There is no friction. Can you solve this orally? Correct. Absolutely. इतना से तो आइडिया लग गया ना कि all that is happening is अगर पुली नहीं होता, sorry, if the pulley did not have mass, तो what would have been the acceleration? If the pulley did not have any mass, खाली g होता. Correct. ठीक है. So because of mass, what is happening is पुली के mass जैसा एक term आ रहा है. All right. So this term has the same dimension as the mass. So because of the mass of the pulley, this is acting as a mass. ठीक है. This is acting as a mass. जिससे इसका acceleration is becoming lesser. So that is what I1 by R1 square, and that is I2 by R2 square. So in all of the results we have seen, check, you'll have this kind of term. In all of the results we have seen. Sub में denominator में, if you remove the pulley, your answer would be the one without I by R square term. And if there is pulley, so basically what is happening? This pulley is not contributing to any acceleration. Alright, this pulley is not contributing to any acceleration. Who is contributing to the acceleration here? mg. Correct? Okay, so in all the cases you will notice that the pulley is not contributing to any acceleration. ठीक है, so what is it contributing to? It is contributing to the mass of the system. तो उससे कहाँ पे फर्क पड़ रहा है? Only in the denominator. ठीक है? Is that clear? Any problem? Okay, so this is very simple. You know how to do this. Okay, so you already know the answer. This would be m2g sin theta, whatever जो भी 45 degree है, sin 45 degree minus m1g sin 45 degree, and this would be divided by m1 plus m2, and this pulley will just act as a mass, and that will be I by R square. Clear? So now you're comfortable writing these equations and relationship between acceleration and alpha in pure rotation. At least that you can find out now easily. Is that clear? Any problem? Okay, so now let's go a step further. Can you rub this off? So what we are going to do is we are going to revisit the hinge. Alright, hinge has some very interesting questions. So this is a rod, it has a mass m and it has a length L, and then it is hinged at this point, at one of the ends. Okay, this is a vertical setup. Okay, so if I release it from here, the rod is going to swing like this. Is that correct? So it has a mass m, length L. Alright, so the question is, initially the rod is at its horizontal position at rest. लिख मत ना, इतना कहानी मत लिख. So rod is at its horizontal position at rest and it is released. Find the instantaneous acceleration of the rod. Find the instantaneous acceleration of the rod. Find the instantaneous acceleration of the rod. Instantaneous मतलब exactly at this moment when I release it. ठीक है, and the force exerted by the hinge. The force exerted by the hinge. ठीक है, देखो इसको कैसे सॉल्व करना है. So first of all, what did we decide when we were dealing with hinge? Assume any force you don't know, so you just assume forces in two mutually perpendicular directions. You know nothing about what kind of force this would be. Okay, so I'm assuming this to be Fy, I'm assuming this to be Fx. Okay, mera man. Okay, now what are the other forces acting on the rod? Mg is going to act like this. Okay, so again there are two things. First of all, what kind of rotation you are going to see? pure rotation, उसमें कोई problem नहीं है. So this is again going to be very easy. Okay. But what are the two things that we need to concentrate on? One is the force equation. The other one is the torque equation. Okay. That is it. Okay. So now let's write the force equation in the vertical direction. Okay. Let's write the force equation in the vertical direction. What will be the force equation in the vertical direction? Let's say that the center, listen carefully. Let's say that the center has an acceleration a. All right. Let's say that the center of this rod has an acceleration a instantaneously. That's what we need to find out. Okay. Let's say that acceleration is a. Okay. So what is the equation we are going to write? Very good. Mg minus Fy should be equal to m into a. Very good. Okay. SA. Okay, this is the setup. All right. Next, can we say something about Fx? Can we say something about Fx? Fx is passing through the center. हाँ वो पता है. उसके अलावा can we say anything about the magnitude of Fx? What kind of force is Fx providing to the rod? चलो भूल जाओ, ठीक है, बाद में करते हैं उसके बारे में. Okay, forget about that right now. Okay, so second thing we need to write is what? Is the torque equation. Second thing we need to write is the torque equation. Okay, so how do we write the torque equation? You're right. You're absolutely right. Fx is going to provide the centripetal force. You're absolutely right. This is what? This is going to rotate. Matlab this is going to go in a circular motion. So the forces which is directed towards the center would be the centripetal force. Correct. You are absolutely right. That brings me to this question. What is the velocity of this center right now? We are talking about the instantaneous acceleration. The velocity is 0. Okay? So does it have any centripetal force? If the velocity is 0, should there be any centripetal force? No. So from here we can say that right now at this instant Fx will be 0. Is that clear? Okay. Next, what should we write? We should write the torque equation. Okay. So about which point should we write the torque equation? About the hinge. Why should we write the torque equation about the hinge? The torque of Fx and Fy will become 0. Okay, always remember this. Whenever we have pure rotation, okay, whenever we have pure rotation, the best strategy is to write the torque equation about the fixed point. Okay? What that'll do is you then don't have to worry about the hinge force. Okay, while writing the torque equation, you'll never have to worry about the hinge force. That'll make it very simple. Okay? Is that clear? Okay. And again I'm saying for pure rotation only. बाद में कैसे deal करेंगे that I'll tell you. Okay, but for pure rotation, always write the torque equation about the point which is fixed. Clear? Okay, so what will be the torque equation? Tell me. So I'm writing the torque equation about this point. What will be the torque equation? mg into L by 2. Okay, the torque equation would be mg into L by 2, and this should be equal to what? This should be equal to I into alpha. Very good. This should be equal to I into alpha. What should I write as I? What should I write as I? ml square by 12 or 3? 12 or 3? 12 or 3? 3. I'm writing the torque equation about which point? I'm writing the torque equation about this point. That means I have to write about this point. Is that correct? So what will be the moment of inertia? The moment of inertia would be ml square divided by 3. Correct? And this should be equal to alpha. Matlab torque is equal to I into alpha. Any problem? So from here m disappears, L gaya. So alpha comes out to be what? 6g upon L. Is my job done? Not really. Is my job done? Not really. Okay, what is lacking here, or what should I find out? क्या? 3 by, ठीक है, sorry, 3g by 12. Yes. So I have found out the angular acceleration. But what do I need to find out? the acceleration. So we need to find out the relationship between the angular acceleration and the acceleration. Is that correct? Okay. तो वो कैसे निकालेंगे? वो कैसे निकालेंगे? वो कैसे निकालेंगे? What is the acceleration of this point? A. What is this length? L by 2. ठीक है. So if this rod has an angular acceleration of alpha, it should have, this point should have an acceleration of alpha r. What is r over here? L by 2. Very good. Okay, so this rod has an angular acceleration of alpha. So if I have to find the acceleration of this point, that acceleration would be what? Alpha into r. And what is r over here? L by 2. And what is that acceleration equal to? A. Okay, so from here what relationship do we get? We get A is equal to alpha into L by 2. Clear? Alpha into L by 2. Okay, now substitute. A is equal to, I'm going to substitute for alpha L. Alpha L अगर substitute कर देंगे तो this will come out to be 3g by 4. Clear? Any problem? Can I rub this off? Okay, so more about hinge later on. It will keep coming in different forms. Okay, so we are done. We are basically done with writing the dynamical equation for pure rotation. Usme koi problem I don't think you'll have. Okay, so we are still discussing pure rotation. All right, so we are discussing different aspects of pure rotation. So what I want to talk about is, I want to talk about the kinetic energy. All right, I want to talk about the kinetic energy of a rigid body, but right now I only want to talk about pure rotation. Okay, let's not complicate matters right now. We are only talking about pure rotation. Okay, okay. When a body is in pure rotation, okay, the kinetic energy of that body is the summation of all the points on the body. Kinetic energy of all the points on the body. Okay, so suppose this is your body. It is rotating like this. Let's say this body is rotating with an angular velocity of omega. So this would be called m1 into r1. This would be rotating like this. This point, this would be called m2 r2, and this would be this will have a velocity like this. This have a velocity like this, and so on. Okay. So the kinetic energy would be the kinetic energy of all those small particles. So can I write it as half into mi into vi square? Okay, half into mi into vi square. So mi is all the small particles on that object. Okay, and vi is their respective velocity. Okay, so what can I find a relationship between v and omega? Can I find a relationship between v and omega? It is rotating with an angular velocity omega. So what is the speed? Omega 1 r1 or omega I ri. So can I write vi as omega I into ri? If I write this, is there any problem? No. So can we substitute it over here? Let's do that. So kinetic energy becomes summation of half mi. What is mi? Mi is mi. And then we have ri ka square, and then we have omega ka square. Correct? From rigid body theorem, what do we know? That the omega of all the particles would be the same. So can I bring this omega square out of the summation? So this becomes omega square into summation of half को भी बाहर निकाल देते हैं. This becomes mi ri square. Does this look familiar to you? What is that? The moment of inertia. So this comes out to be half I omega square. Half I omega square. And this is very easy to remember because the kinetic energy for translation is half mv square. So m ki jagah you will have I, and omega ki v ki jagah you will have omega. Correct? One very important thing. This I is about the axis of rotation. ये मत भूलना. This I we have calculated is about what? Is about the axis of rotation. So whatever is the nature of rotation of the object, if it is in pure rotation, we are writing the kinetic energy as half I omega square. But I about what? I about the axis of rotation. ठीक है? If it is asked the kinetic energy, नहीं वो अभी नहीं पूछा जाएगा, don't worry. ठीक है? So for a purely rotating object, the kinetic energy is half I omega square, but that I is about the axis of rotation. Is that clear? Any problem? Okay. We can draw one or two more analogies related to this. What is that? We know that the work is equal to the integral of f dot dr. The work is equal to integral of f dot dr. Okay. So just drawing the analogy, can we write about the work done by a torque? Can we write it like this? Okay, we can write it like this. Okay, this is not a different kind of work. It is derived from here itself. Okay, all these equations that we are writing in rotation, all these equations that we are writing in rotations are not independent equations. They're not derived from some other concept. All of them are being derived with the same concept which we have used for translation. ठीक है? यहीं से we'll take a cross product और ये answer आएगा. I'm not deriving it. काम नहीं है उसका. But the work done is the same. This is work done by all the forces. ठीक है? Integral of tau dot d theta. Now it's very simple. If torque is clockwise and the rotation is anti-clockwise, the work done would be negative. Right? So if the torque and the angle of rotation or the angular displacement are in opposite direction, the work done would be negative. If they're in the same direction, the work done would be positive. Okay? Is that clear? Okay, if that is clear, can I rub this off? If that is clear, then can we also talk about the conservation of energy? Yes, we can talk about the work energy theorem. We can talk about the conservation of energy of a rotating object. Okay? Nothing changes there. The equation is still that same equation. What is that equation? Work done by external plus work done by non-conservative is equal to delta k plus delta u. Nothing changes. Okay? Only the term which contains the kinetic energy will have to take care of the rotational kinetic energy, and the term which takes care of the work done should take care of the work done by the torque. That's it. Is that clear? Nothing else. Okay? So let me give you a very simple problem. Mass m, length L. This rod is hinged about this point. Okay? Now it is released from this point. It is released from this point. When it becomes vertical, the question is find the angular velocity of the rod. When it becomes vertical, find the angular velocity of the rod. Okay, when it becomes vertical, find the angular velocity of the rod. Okay, so what we have to think is again in terms of work energy theorem or conservation of mechanical energy. So first of all, how do we decide we can conserve mechanical energy or not? How do we decide? The work done by the external force should be 0 and there should not be any non-conservative forces. Okay? There is hinge force. Okay, now you decide, is the hinge force conservative or external? Would you categorize the hinge force to be non-conservative or external? Why non-conservative? Why non-conservative? Friction kidhar hai? Did I say that this hinge has friction? There is no friction. Okay, we are not assuming friction right now. ठीक है. So there is no friction in the hinge. So what is the work done? What is this hinge force? We'll categorize it as the external force. ठीक है. First of all, what is my system? What is the system? The rod and the earth. We'll take the system as earth plus rod. ठीक है. What are the external forces? ठीक है. The hinge force. The external force is the hinge force. Is the hinge force doing any work? Why not? No displacement of the axis. Obviously it is fixed. So the hinge force is not doing any work. So can we conserve mechanical energy? Obviously we can conserve mechanical energy. Is that correct? Okay. So let's write the equation for conservation of mechanical energy. So basically what is happening? So first of all we have to write the gravitational potential energy. For that we need to choose a reference. ठीक है. वो रेफरेंस को भी गोली मारो यार, आप उतना बच्चे जैसा नहीं करेंगे. सिंपली इट वाज हियर, इसका सेंटर वाज हियर, नाउ इसका सेंटर इज हियर. सो देयर हैज बीन अ लॉस इन ग्रेविटेशनल पोटेंशियल एनर्जी एंड दैट विल गो इनटू द गेन इन काइनेटिक एनर्जी. सो टेल मी हाउ मच हैज द काइनेटिक एनर्जी पोटेंशियल एनर्जी गॉन डाउन बाय mgl/2. ठीक है. व्हाट इज द हाइट इट हैज कम डाउन? l/2. सो द लॉस इन ग्रेविटेशनल पोटेंशियल एनर्जी इज mgl/2 and that should be equal to the gain in kinetic energy. Alright, the gain in kinetic energy. So this rod is in pure rotation or not? It is in pure rotation. So I should write half I omega square. I should write half I omega square. What should I write I as? ml square by एक्सिस कौन सा है? हाँ, एक्सिस मतलब समझता है? दिस इज द एक्सिस ना, मतलब I'm confused now. Do you understand the meaning of axis of rotation? Right, this point, it is rotating about this point. Correct, so that is the axis of rotation. So we have to find the moment of inertia about this axis. How much is that? ml square by 3. ml square by 3. So this gets cancelled, m gets cancelled, this gets cancelled. So omega is equal to how much? 3g by l ka under root. Okay. What about torque? What about torque? Torque is also there. हाँ, तो so why should we incorporate torque in energy conservation? Do we consider any force when we are dealing with energy conservation? मतलब we are worried about the work done by the forces in energy conservation, right? तो यहाँ पे which torque is doing work? Torque of which force is doing work? Tell me. mg, and mg is in my system. mg is already in my system. So work done by the gravitational force is incorporated in the potential energy term. Clear? Any problem? ठीक है. The spring is initially unstretched. The spring is initially unstretched. The question is, find the maximum elongation of the spring. Find the maximum elongation of the spring. Will the pulley rotate? Why should it not rotate? तो यहाँ तो स्प्रिंग लगा है. Okay. Mm. So you are telling me the pulley would not rotate. That's what you're telling me. Let me see. Mm, the pulley. देखो, if the length is changing, तो ज़रूरी नहीं है कि then length is only going to change from this side. ठीक है, this entire length is now variable. ठीक है, because the string is connected to the spring, this entire length is variable. तो इधर से भी चेंज हो सकता है, इधर से भी चेंज हो सकता है. राइट, सो द पुली शुड रोटेट. पुली के रोटेट करने में तो कोई प्रॉब्लम नहीं होना चाहिए. ओके, दिस पार्ट, हाँ. यस, यू आर राइट. यू आर राइट. ठीक है, तो लेट मी चेंज द क्वेश्चन. यू आर राइट. इफ इट हैज टू रोटेट, यहाँ से तो कुछ फ्री होना चाहिए. ठीक है, यू आर राइट. लेट्स चेंज द क्वेश्चन. लेट्स चेंज द क्वेश्चन. अब कोई प्रॉब्लम? The question is, find the maximum elongation of the spring and the maximum kinetic, the maximum speed of small m. The maximum speed of small m. Two mg by k. Correct. Find the maximum speed of small m. वो भी question है. Find the maximum speed of small m. मालूम नहीं. So did you calculate the maximum elongation? वो निकल गया क्या? Maximum elongation में कोई problem नहीं होगा क्योंकि उसमें rotation का कोई term ही नहीं आएगा. Okay, so let's say this goes down by a distance x. Maximum elongation matlab if it has gone down by a distance x, it comes to a stop over here. If this comes to a stop, the pulley will also stop. ठीक है. So what is the loss in gravitational potential energy? The loss in gravitational potential energy is mgx. ठीक है. And that has gone into the gain of what? Spring potential energy. Has that loss in gravitational potential energy gone in kinetic energy? No. This block was initially at rest, finally at rest. This pulley was initially at rest, finally at rest. So there has been no gain in kinetic energy. Correct? So all that loss in gravitational potential energy has gone into the gain in spring potential energy. ठीक है. तो यहाँ से x you will get as 2 mg upon k. No problem. Okay. Now the question is, what will be the maximum kinetic energy or maximum speed of this block? At the mean position. Very good. At the mean position. So can you tell me where is the mean position? Correct. Correct. Absolutely right. So we have already seen this in multiple cases and we have seen this in SHM also. That uska equilibrium kahan pe aayega? So suppose the block was here, that's the natural length of the spring. So if I leave it, equilibrium, where will the equilibrium be? Where the net force is 0. Net force kab 0 hoga? When this is mg and this is kx. Okay, dhyan do. This would be kx. This is the tension in this side of the string. So how can I say that idhar bhi kx hoga when this pulley has mass? It is like two block problem. ठीक है, that is not my question. My question is, the spring is elongated by x. This goes down by x. Let's say call it x naught. This goes down by x naught. The pulley is elongated by, sorry, the spring is elongated by x naught. So the force exerted by the spring is kx naught. So that is the tension on the left string, left part of the string. I am saying that the tension on the right part of the string is also kx naught. ये कैसे? The pulley has mass. How can I say that the tension on both sides will be the same? क्या? नहीं समझ में आया question. Did you get the question? हाँ? Yes, तो ऐसा बोलना. When we are saying that this block is in equilibrium, मतलब this pulley would also be in equilibrium. Yes or no? ठीक है, we leave it like this so that it is at rest or it is stationary. We bring it over here and we release it. ठीक है, so this block is in equilibrium. If this block is in equilibrium, this pulley will also be in equilibrium. So that is why we can say that the tension on both sides would be the same. Clear? ठीक है, so what will be your equilibrium position? The equilibrium position would be mg इज इक्वल टू के एक्स नॉट, यानी एक्स नॉट इज इक्वल टू क्या, एम जी अपॉन के. इज दैट क्लियर? ठीक है. So that means that the block will have maximum kinetic energy when it has gone down by mg by k. Clear? Now can you find out the maximum speed? How would we calculate the maximum speed? Energy conservation करेंगे. Alright, energy conservation. Okay, let's see. So when this block reaches this point, let's assume its speed to be v. ठीक है, let's assume its speed to be v. Okay, so the loss in gravitational potential energy is mg into x naught. This is x naught. So the loss in gravitational potential energy is mg into x naught. And what is x naught? mg by k. So that loss in gravitational potential energy has gone into what? That has gone into the kinetic energy of this block. That has gone into the kinetic energy of this pulley. And that has also gone into the potential energy of the spring. Okay? So this mg into x naught should be equal to half k into x naught square. Half k into x naught square plus the kinetic energy of the block. How much is that? Half mv square. That's the kinetic energy of the block, plus half I omega square, because this is pure rotation. The pulley is in pure rotation. So half I omega square. What are the things we don't know? What are the things we don't know? We don't know omega and we don't know v. So there are two variables. Can I find a relationship between v and omega? Omega is equal to v by r. कहाँ से मिला वो relationship? Constraint equation. Excellent. So this has a velocity v. मतलब we'll assume that it has some angular velocity of omega. So this point will have a speed of omega r. Correct? This point will then have a speed of omega r. And this point has a speed of v. Shouldn't both be equal? Okay? So the same way we got a is equal to alpha r, exactly the same manner we are getting v is equal to alpha r. Correct? So from here we are going to get, sorry, v is equal to omega r. So we can substitute omega by v by r. Can we do that? Okay? So we are going to substitute omega by v by r. Now it's done. So ये कितना आ जाएगा? This will be, इसको इधर ले आएंगे तो this will become half m g square by k, m square g square by k is equal to half m plus half I by r square into v square तो ये हाफ ये हाफ ये हाफ गया. So V is equal to m square g square divided by k into m plus I by r square का अंडर रूट. इट विल बी, इट इज इन इक्विलिब्रियम. इक्विलिब्रियम का मतलब रेस्ट होता है क्या? हाँ, गुड. इक्विलिब्रियम मतलब नेट टॉर्क इज जीरो बट डज नॉट मीन इट इज एट रेस्ट. क्लियर? एनी प्रॉब्लम? ठीक है. सो अभी तक क्या हुआ है? अभी तक ज्यादा कुछ चेंज नहीं हुआ है. द ओनली थिंग वी नीड टू अंडरस्टैंड इज दैट अपार्ट फ्रॉम ट्रांसलेशनल काइनेटिक एनर्जी वी ऑल्सो हैव टू टेक केयर ऑफ द रोटेशनल काइनेटिक एनर्जी. दैट्स इट. अभी और कुछ भी कॉम्प्लिकेट नहीं हुआ है. इट्स एग्जैक्टली द सेम. क्लियर? Okay, so this rod has a mass m and length L. It is like this initially. We push it slightly, very slightly. मतलब we release it from here. इसका मतलब है when it is released from here, it will not have any velocity. ये मतलब it is slightly pushed. ठीक है? When it is slightly pushed, at some time this will be like this. It comes down like this. ठीक है? So the question is, find the angular velocity of the rod and the force exerted by the hinge. Find the angular velocity of the rod and the force exerted by the hinge. हाँ, angular velocity and root over 6g by L probably. G हाँ, root over g हाँ, correct, root over 6g by L. एंगुलर वेलोसिटी. वेलोसिटी निकालना होता तो कोई यूनिक वैल्यू बता पाता क्या? नहीं. दैट विल चेंज विद द पॉइंट. 12 mg upon L square. कैसे निकाला? Hinge force will contribute to the centripetal force. ठीक है, and then what did you take the radius? L by 2. Correct, सही किया. Good. ठीक है, so ओमेगा निकालने में किसी को कोई प्रॉब्लम है? ठीक है, that is simple. By how much has the center come down? L. So the loss in gravitational potential energy is mgl. And since this is pure rotation, we are going to write half I omega square. What will be I? ml square by 3. Half I omega square. Okay? So this goes away. So we get omega is equal to 6g upon L का under root. Okay? Okay. Now let's talk about the forces. Let's talk about the forces. मेरे को आंसर तुम्हारा नहीं पता है, but you what you said was correct, but let's see if you have applied it correctly. Probably कुछ गड़बड़ हुआ होगा, probably, because probably तुमने ये नहीं लिया होगा. Okay, so the hinge force right now. Okay, so when it is in this vertical position, the forces acting on it is mg and F. Is there any other? And are we sure that the hinge force is only going to act upwards? Are we sure that the hinge force is only going to act upwards? Why not? Why aren't we sure? Yes or no? So hinge force, we know that hinge force is, we cannot really say that what will be the direction magnitude of the hinge force. Okay, so we generally what we do is we write an fx and when we write an fy, correct? Okay, but in this particular case I'm talking about, can we say that there would be no force in the hinge in the horizontal direction? Yes or no? Why can we say that? नहीं, वो रीज़न नहीं है. ठीक है, so hinge force basically क्या है? Normal force ही है ना. ठीक है, hinge force is basically a normal force. Normal force is what kind of force? It's a self-adjusting force. Normal force is a self-adjusting force, like tension, like friction. So until there is a force in a certain direction, normal force would not be there. So do you see any force in the horizontal direction at this position? Do you see any force in the horizontal direction? No. So why should normal force come here, or why should hinge force come here in the horizontal direction? Correct. If I start pushing it like this, if I start applying a force like this, then there would be a hinge force in the horizontal direction. It's a self-adjusting force. Is that correct? So right now we are absolutely sure there will be no horizontal component of the hinge force. Do you agree? Any problem? Okay. So we are talking about now the circular motion of the rod. Okay. And which point of the rod? We are talking about the center of mass of the rod. Okay. We are talking about the center of mass of the rod. Okay. So this center of mass of the rod is moving in a circle of L by 2. So the net centripetal force should be equal to mv square by r or m omega square r. Do you get that? So what is the net force towards the center? Very good. The net force towards the center is not just this hinge force, but also mg in the opposite direction. So the net force towards the center is F minus mg, and this should be equal to what? M omega square. What is omega square? 6g by L into r. What is r? L by 2. Is that correct? Any problem? Okay. So for this object, we can assume that this object is concentrated at its center. Circular motion के लिए ये काम हम लोग कर सकते हैं. That this object is concentrated at its center of mass, and then we can write the circular motion equation considering a point mass situated at its center of mass. We can do that. Is that clear? Any problem? Okay. So this will come out to be what? This will come out to be 4mg. Clear? Any problem? Very good. Can I rub this off? ठीक है. So if you notice, we are gradually moving towards more complexity. With every problem, we are incorporating some more complexity, right? Okay, so let's complicate matters a little more. ठीक है. So at some instant, हाँ हाँ हाँ, m omega square r. You either write mv square by r or you write m omega square r. mv square by r or m omega square r. ठीक है. So we have already calculated omega, so I'm writing m omega square r. ठीक है. So we release it from a horizontal position. At some instant it is going to make an angle of 45 degree with the horizontal. ठीक है. So the question is same. Find the angular velocity and also find the angular velocity and also find the hinge force. Find the angular velocity and also the hinge force. Hmm. L by 2, ये कैसे हीरो? mg L by 2 कैसे? mg L by 2 cos 45 डिग्री. हाँ देखा. mg L by 2 into 1 by root 2 is equal to half. हाँ ठीक है, करेक्ट. hinge force. 5 mg/2 कैसे आया? F इज इक्वल टू क्या किया, m ओमेगा स्क्वायर L/2 प्लस बस. सो दिस यू हैव रिटन इज सेंट्रीपिटल फोर्स का इक्वेशन है ना. और कुछ और कुछ श्योर mg cos 45 ही होगा. सोच सोच आराम से सोच, हड़बड़ाने की जरूरत नहीं है. कुछ तो किया है. ओके एफ एक्स माइनस एम जी रूट टू इज इक्वल टू m ओमेगा स्क्वायर r एफ एक्स एंड देन एफ वाई निकाला mg/4. वाई डू यू थिंक एफ वाई वुड बी mg/4? अल्फा निकाल लिए. ओके अल्फा निकालने में थोड़ा गड़बड़ कर दिया है तो mg तो would be like this. ठीक है बट यहाँ बट वेरी गुड अटेम्प्ट. तो mg L/2 इंटू 1/√2 दैट विल बी इक्वल टू i इंटू अल्फा. अल्फा निकाला, a निकाला, एक्सीलेंट, वेरी गुड अटेम्प्ट. ठीक है एक्सेप्ट दैट तू वो टॉर्क इक्वेशन लिखने में गलती किया, अदरवाइज एक्सीलेंट अटेम्प्ट. नहीं उससे पहले एक बार मेरे को वो लास्ट इक्वेशन दिखा दे. लास्ट इक्वेशन एज इन वो इक्वेशन अल्फा निकाला ना तू. सो ए निकाल लिया बट दिस ए बैठ दिस ए. ठीक है सो यू हैव टू अंडरस्टैंड दिस ए इज इन दिस डायरेक्शन. तो इस डायरेक्शन में इज द नेट फोर्स एफ वाई. एक बार वो सोच ले. This is the direction of acceleration, so the net force in this direction should be mass into acceleration. So are you sure that the next net force in this direction is Fy? नहीं ना. तो इसमें थोड़ा सा गड़बड़ है, वो चेक कर. देखो slightly complicated problem, but I'm saying slightly because nothing concept wise has changed, nothing at all. I'll show that to you. Nothing has changed concept wise. Okay, we'll go step by step. We'll see what is the phenomena and we'll see how to go about it. It's a set procedure to do this, right? First of all, can you find the angular velocity at this point? Everyone could. Okay, so what was the angular velocity? Tell me. Root over of 2 root 2L. ठीक है, this was the angular velocity. ठीक है, that's very simple to find out. ठीक है, mg into L cos 45 degree is the loss in gravitational potential energy. That should be equal to half I omega square. I would be ml square by 3. ठीक है, okay, so you found omega. When you have found omega, now look at this rod in this position. Look at this rod in this position. तुम ही लोग कैलकुलेट कियो यार, ये होगा, ठीक है, ओके. Now tell me, this rod does it have centripetal acceleration? Does it have centripetal acceleration? How do you know it has centripetal acceleration? It is going in a circle and it has a velocity at this point. So this rod certainly has a centripetal acceleration. Okay. Does this rod have a tangential acceleration? Anything goes in a circle might have a centripetal, must have a centripetal acceleration. It might have a tangential acceleration. When will it have a tangential acceleration? When omega would change. If omega changes, there is tangential acceleration. Okay, so is omega changing or not? We are talking about at this instant. We are talking about at this instant. When would something have alpha? When there is an external torque. If at this instant there is an external torque, it will have alpha. Okay, so does this have any alpha at this point? Iska matlab, yes or no? Does it have any external alpha? External torque. Hinge force is here. mg to act karega na dost. mg is going to act vertically downwards. Capital mg likhe hain to theek hai. This mg, does it have a torque about this point? Yes or no? Okay, so what we can do is, since this is pure rotation, we can think of torque about the point which is fixed. So we are going to calculate the torque about this point. So does this rod have torque about this point, torque of mg about this point? Yes or no? Obviously it has. So does it have torque or not? Torque is acting on it, external torque is acting on it. So should it have alpha or not? It should have alpha. So if it has alpha, should it have tangential acceleration or not? Obviously. Do you get that? Is that clear to everyone? Okay. So I'm saying that again. Okay, this rod is over here, it is in circular motion, so it must have centripetal acceleration. And at this point it has torque acting on it, so it must have alpha, because at every point dekho omega is going to change. हाँ कि ना? From here it has 0 omega. At this point it will have some different omega. At this point it is going to have some different omega, right? So omega is continuously going to change. Why? Because there is a torque acting on it. Okay? So if there is a torque acting, it has alpha. If it has alpha, it has what? It has a tangential acceleration. Correct? Okay. Now how do we deal with an object which has both centripetal acceleration and tangential acceleration? How do we deal with that? How do we deal with that? Write equations. Before writing equations, what do we do? Resolve every force along the direction of, or towards the center. Resolve all the forces towards the center and perpendicular to the center. Abhi tak we are already going, or we are just going on the set procedure. We have just found out that it has a centripetal acceleration and tangential acceleration. If something has a centripetal acceleration as well as a tangential acceleration, what do? We resolve all the forces towards the center and away and perpendicular to the center. Correct? And then we write the force equations or the acceleration equations. Correct? Okay. So I'm going to resolve this as mg cos 45 degree and this as mg sin 45 degree. मतलब एक ही बात है यार, 45 degree तो does not matter. ठीक है? Is that correct? Okay. Now this hinge force, I don't know what is the direction of hinge force, but I can, whatever be the direction of hinge force, I can always resolve it into mutually perpendicular directions. So it is very convenient to resolve it in these two directions, obviously, because we have to resolve all the forces along the direction of, along the center and perpendicular to the center. Correct? Any problem? Okay. Now this rod has a centripetal acceleration. So what can we write for the equation of centripetal acceleration? Fx minus mg sine 45 degree should be equal to m. What is omega? 3g upon root 2l m omega square into r. What is r? R is L by 2. Is that correct? So fx I have found out. fx में निकालने में कोई दिक्कत नहीं हुआ. Is that correct? Okay. Now we have to think about fy. Okay. Now we have to think about fy. Step by step. Step by step. ठीक है. So this rod, let's say, this rod is moving, this is rotating like this. So this center will have an acceleration in this direction. Correct? This center is going to have an acceleration in this direction. Take it. So what can we write for the perpendicular direction? Can we write an equation for the perpendicular direction? What equation can we write for the perpendicular direction? mg cos 45 degree minus fy is equal to m into a. Can we write that? Abhi bhi we have not done anything new. Do you agree? Acceleration is direction mein hai, so we'll write the force equation for this one. Is that correct? Any problem? Okay. Now we have to find this tangential acceleration. To find tangential acceleration, what do we need? So this is rotating. We need to find the tangential acceleration. To find the tangential acceleration, what do we need? What do we need? To find tangential acceleration, what do we need? Alpha. और क्या होगा? To find tangential acceleration, what do we need? Tangential acceleration is equal to alpha r. So to find the tangential acceleration, we need alpha. And how do we calculate alpha? By torque. So ultimately everything is leading to torque. Do you get that? Okay. So how do we find torque? We are going to find the torque about this point. Why this point? Because it is fixed. So we are going to find the torque about this point. Okay. So what will be the torque? mg sin 45 degree का कोई torque नहीं होगा. mg cos 45 degree का torque होगा. So the torque at this point would be mg cos 45 degree multiplied by L by 2. That is the torque. And this should be equal to I into alpha. What should I write as I? Very good. ml square by 3. इस point के बाद torque लिख रहे हैं. So m L square upon 3 into alpha. So this goes away. So alpha comes out to be what? Alpha comes out to be what? 6g Is that all right? Any problem? Very good. So we have found out alpha. When we have found out alpha, can we find out a? So a would be equal to what? A will be equal to alpha multiplied by L by 2. This radius is L by 2. So this will be equal to L by 2, मतलब ये हो जाएगा 3g divided by root 2. ठीक. तो ये 6 ऊपर गया और ये रूट 2 यहाँ पे है. ठीक तो है? Oh my bad. तो अल्फा इंटू एल बाई टू 3/4 रूट 2. अब ठीक है. अल्फा एल बाई 2. हाँ अब ठीक है. ठीक है. ओके. सो दिस इज द एक्सेलरेशन. विच एक्सेलरेशन? द टेंजेंशियल एक्सेलरेशन. Now can we substitute this over here? So this is going to give us mg cos 45 degree, or we can write directly fy is equal to mg cos 45 degree minus m into a. So that is going to be 3 mg upon 4 रूट टू, तो ये आ जाएगा mg अपॉन रूट टू माइनस 3 mg अपॉन 4 रूट टू। 4 से ऊपर नीचे मल्टीप्लाई डिवाइड करेंगे तो आ जाएगा mg अपॉन 4 रूट टू। So that is fy. fx have we already calculated? fx we have already calculated. ठीक है? So now you can find the hinge force and that will be equal to fx square plus fy square under root. जो भी आता हो, जो भी आता हो. So I chose this angle randomly. Okay, I chose this angle randomly. Probably 30 डिग्री या 60 डिग्री या प्रॉब्ली 37 या 53 लेता तो कैलकुलेशन थोड़ा रूट टू नहीं आता, वो होल नंबर्स आता, कट जाता. ठीक है, एनीवे, डू यू गेट द कॉन्सेप्ट? ठीक है, एवरीथिंग दैट हैज बीन अप्लाइड ओवर हियर वी ऑलरेडी नो, इट्स जस्ट अबाउट पुटिंग इट टुगेदर. Correct? We have to think logically, we have to think sequentially. If something is rotating, it is in circular motion, its center is in circular motion, so it is going to have two kinds of accelerations. It might have two kinds of acceleration, the centripetal acceleration, the tangential acceleration. Now since it has an external torque, we know that it has tangential acceleration, so we are going to resolve all the forces along the direction of center and perpendicular to center. Then we write the equation for the centripetal force, then we write the equation for the tangential force. We don't know tangential acceleration, so for tangential acceleration we need alpha, for alpha we need torque. We find alpha, we find a, substitute, done. Clear? Any problem? ठीक है, can I rub this off? इस क्वेश्चन में आगे मजा आता है जब this is kept on a ledge like this, फिर फ्रिक्शन भी आ जाता है, फिर और मजा आता है. ठीक है, दैट बट लेटर ऑन, अभी नहीं. Everything is which is has been applied is all that things we have already know. We have already studied all these things in detail. चलो ठीक है. Okay, now let's do something very simple. थोड़ा heavy हो गया probably. Okay, now let's do something very simple. Again we just have to draw analogy between translational motion and rotational motion. ठीक है, तो जैसे we have something known as linear momentum, we have something known as angular momentum. ठीक है, angular momentum first of all we defined for a point. We are defining the angular momentum for a point. ठीक है, suppose this is the point O. There is an point object which has a mass m and which has a velocity mv, velocity v, so it has a momentum of mv. ठीक है, now we join it with a point r. ठीक है, we join it with a point r. Okay, so this has a linear momentum of mv. So angular momentum is denoted by small l. Angular momentum for a point is denoted by small l, and angular momentum is defined as moment of linear momentum. Is defined as moment of linear momentum. Do you understand the meaning of moment? Moment of a force we calculated or not? Did we calculate the moment of a force? What was that? Torque. The moment of a force was torque. तो इस mv की जगह अगर f रख देते तो moment of force क्या होता? r cross f. So instead of this force we have kept here linear momentum. So if now we do r cross mv, what do we get? We get the moment of the momentum, moment of the linear momentum. ठीक है, and that is known as the angular momentum. ठीक है, so angular momentum is defined as r cross mv. Clear? mv is the linear momentum, r cross mv matlab the moment of the linear momentum, and that is the angular momentum. Is that clear? ठीक है, nice moment. L is equal to r cross mv. ठीक है, अब ये कैलकुलेट कैसे करना ये बताने की हमको जरूरत नहीं है, बिकॉज यू ऑलरेडी नो हाउ टू कैलकुलेट आर क्रॉस एफ. एक्सटेंड द लाइन ऑफ एक्शन, ड्रॉप अ परपेंडिकुलर, या इसको रिजॉल्व कर दो दिस परपेंडिकुलर इनटू दिस लेंथ, और अगर एंगल पता है तो एंगल से निकाल दो. ठीक है, द वे यू हैव बीन कैलकुलेटिंग द टॉर्क वैसे इसको कैलकुलेट करना है. इंस्टेड ऑफ फोर्स व्हाट यू हैव द लीनियर मोमेंटम. ठीक है, दिस इज द एंगुलर मोमेंटम फॉर अ पॉइंट ऑब्जेक्ट, एंगुलर मोमेंटम फॉर अ पॉइंट मास. ठीक है, ऑब्वियसली नाउ वी आर डीलिंग विद व्हाट, रिजिड बॉडी. Now we are talking about angular momentum of a rigid body, and we are talking about pure rotation only. Pure rotation. ठीक है, we are only talking about an object which is in pure rotation. Okay, so I'm not deriving that. ठीक है, उसका derivation if you want you can see anywhere. It's not required for you, but I'm giving you the result. उसका angular momentum is given by L is equal to I omega. This angular momentum is given as L is equal to I into omega. Analogy, absolutely. What do we write the momentum as? We write the momentum as m into v. So the angular momentum of a rigid body in pure rotation, ध्यान में रखना, in pure rotation. Pure rotation अगर नहीं होगा, rotation with translation होगा, तो इसमें और कुछ खतरनाक terms add हो जाएंगे. बट अभी के लिए लेट्स कीप इट सिंपल, L इज इक्वल टू आई ओमेगा. ठीक, दैट्स इट, नथिंग एल्स. ओके, अगेन आई किसके अबाउट होगा? यस, वेरी इंपॉर्टेंट. इफ इट इज इन प्योर रोटेशन एंड वी आर राइटिंग L इज इक्वल टू आई ओमेगा, आई इज अबाउट द एक्सिस. ठीक, नीडलेस टू से एंगुलर मोमेंटम इज ऑल्सो अ वेक्टर क्वांटिटी which will have the same direction as omega. So either clockwise, either anti-clockwise. ठीक, any problem? Okay. So do we know about the conservation of linear momentum? When is the linear momentum conserved? When there is no external force. Very good, because how we define force? We define force as dp by dt. If there is no external force, the linear momentum is conserved. So without even deriving it, can we draw the analogy between torque is equal to dl by dt? Very good. And obviously external torque. ठीक है, so all these things, because I can take straight analogies, I don't have to derive it also. ठीक है, the torque external is equal to what? dl by dt. So if there is no external torque on an object, what will happen? The angular momentum will be conserved. Is that correct? So if you know the condition for conservation of linear momentum, you also know the condition for conservation of angular momentum. ठीक है? So if there is no external torque in object, the angular momentum will remain constant. Is that clear? Any problem? Very good. Can I rub this off? Okay, more analogies. ठीक है, it's because it'll make it very simple for you. ठीक है, अगर ये सॉल्व करना आता है लीनियर में, तो एंगुलर में ऐसे ही सॉल्व करना है, कोई स्ट्रेस नहीं है. ओके, ये सब क्वेश्चन याद है क्या? ठीक है, सो दिस इज अ फ्रिक्शनलेस प्लेटफॉर्म, उस पे देयर इज समवन विद मास m. he jumps off u with a velocity u with respect to platform. So this is with respect to the initial velocity of the platform or the final velocity of the platform? It jumps with a velocity u with respect to the platform. This is given to you. It is, so this u is with respect to the initial velocity of the platform or final velocity of the platform? Final velocity of the platform. If it is not given, it is always with respect to the final velocity of the platform. ठीक है? Okay. So इसमें क्या हम लोग पूछते हैं? Find the velocity of the plank. ठीक है? Do you know how to solve it? obviously you know how to solve it, but still बता दे रहे हैं, ठीक है, still बता दे रहे हैं, ठीक है. So initially the linear momentum of the system was 0, so finally also the linear momentum of the system has to be 0. So I'm going to write m1 v1 plus m2 v2 is equal to 0. v1 is the final velocity of particle 1, v2 is the final velocity of particle 2, ठीक है. And we can conserve linear momentum from which frame? From the ground frame. We can only conserve linear momentum in this case from the ground frame. So this v1 and v2 is required from where? From the ground frame. Okay. So for this what do? We assume a direction. Let's say we say that the right hand side is positive. Okay. And we assume that the velocity of the platform will become v. The final velocity of the platform is v. Is that correct? Okay. Now what do? We insert it in that equation. m1 is small m. Now this v1 is with respect to what? Ground. This u is with respect to the platform. So with respect to ground, the velocity would be u minus v. Velocity of this guy with respect to platform plus velocity of platform with respect to ground, keeping the directions in place. So u is positive, this is negative. So we are going to write u minus v plus m2 is capital M, and we'll write minus v equal to 0. So v comes out to be mu upon m plus m. ठीक है, standard result. बहुत बार किया है. Is that correct? ठीक है. So if you remember this, you'll have no problem solving questions on angular momentum, conservation of angular momentum. ठीक है. Let's try a few problems. Can I rub this off? ये तो याद ही होगा probably. तुम लोग नहीं पढ़े हो, ठीक है, कोई बात नहीं. Okay, so I'm showing you a top view. Okay, so there is a disc, or you can say a platform, which can rotate about this vertical axis. Okay, I'm showing you the top view. Okay, initially it is at rest, and then there is a guy with mass small m. Iska moment of inertia I, radius r, and this guy is standing on the periphery, and this guy starts moving with an angular velocity omega with respect to the platform. Okay, this guy starts moving along the periphery with an angular velocity omega with respect to the platform. Did you get that? Okay, so the question is, find the angular velocity of the platform. The question is, find the angular velocity of the platform. Do you understand that the previous problem and this problem are exactly the same? अब ट्राई करो. क्या बात. करेक्ट वही होगा, बट अब सॉल्व कर ले. You're right. देखो, I'll solve this one for you. Okay. So this guy starts moving anti-clockwise. So are we sure that the platform is going to move clockwise? Pretty much sure. So let's say that the platform starts moving in the clockwise direction with an angular velocity omega prime. Okay. Which direction you want to take positive? You want to take anti-clockwise to be positive. ठीक है, चलो मान लो. All right. Okay. So what is the initial angular momentum of the system? What is the initial angular momentum of the system? 0. Both of them were at rest. So what should be the final angular momentum of the system? 0. Okay. Because there is no external torque acting. The force that it applies, or the torque that is being applied on this, is an internal torque. Okay? There is no friction anywhere. There is no there aren't any other forces. Okay? So the angular momentum will be conserved. Correct? Okay. So let's find out the angular momentum of both these objects with respect to ground. Okay? Again, with respect to ground. If this guy is moving with an angular velocity omega and this platform is moving with an angular velocity omega prime, the angular velocity of this guy with respect to ground is what? Very good. So if we look from the ground frame, this guy over here will have an angular velocity of omega minus omega prime. That omega is with respect to the platform. So that is omega minus omega prime. Now this guy is a point object. Okay? This guy is a point object. So we can find its angular momentum in two ways. Okay? I'll show both the ways. What do we have? We have the angular momentum is r cross mv. Or we can say the momentum into the perpendicular length. Correct? The momentum multiplied by the perpendicular length. So if this guy is over here, what is the direction of the velocity? The direction of velocity would be like this, tangential. So what is the velocity of the particle, or what is the velocity of this person into r? Okay. So the velocity of this person is equal to omega minus omega prime multiplied by r. Tick. So this is the direction of momentum also. And is this the perpendicular length? Yes. So the angular momentum becomes what? The angular momentum becomes mv into r. mv into r perpendicular. Do you get this? Or should I explain more? ठीक है, चलो देख लो. देख लो, if you have confusion देख लो. So this particle is going in a circle with angular velocity omega. This particle is going in a circle with angular velocity omega. So the speed at any point would be equal to omega r. And if we drop a perpendicular from here, this becomes the moment arm. So what will be the velocity? What will be the angular momentum? Momentum multiplied by r perpendicular. So mvr. And probably this you have done in Bohr's model. उसका angular momentum लिख देते थे mvr. Obviously उसको पता नहीं होता था क्यों लिखते थे. ठीक है, केमिस्ट्री वाले थोड़ी तो बताएंगे क्यों लिखते हैं. ठीक है, v omega r and r perpendicular. So the angular momentum is mvr. ठीक है, this we are going to use a lot of times. mvr. ठीक है, if the velocity is perpendicular to the radius, the angular momentum would be mvr. ठीक है, this we are going to use a lot of times. Is that clear? इसको एक दूसरे तरीके से भी कैलकुलेट कर सकते थे. कैसे? This we can take as an object. ठीक है, what is the moment of inertia of this guy about this point? The moment of inertia is mr square. What is the angular velocity? So the angular momentum we can also write it as, दोनों चीज सही है. ठीक है, अगर पॉइंट ऑब्जेक्ट है तो उसके लिए यू कैन राइट आई ओमेगा, यू कैन राइट आर क्रॉस एम वी, डज नॉट मैटर. इज दैट करेक्ट? ठीक है, बट द क्रक्स इज वी आर एबल टू फाइंड आउट द एंगुलर मोमेंटम ऑफ दिस पर्सन विद रिस्पेक्ट टू द ग्राउंड. कैन वी डू दैट? ऑब्वियसली वी कैन. क्लियर? एनी प्रॉब्लम? Okay, so I'm going to write the angular momentum as m r square into omega minus omega prime plus, now I have to write the angular momentum of what? Angular momentum of the platform. ठीक है, This plus the angular momentum of the platform. What should I write the angular momentum of the platform? I into minus omega prime. Very good. I into minus omega prime. So this will become minus I omega prime, and this should be equal to 0. तो यहाँ से ओमेगा प्राइम क्या आएगा? यहाँ से ओमेगा प्राइम will come out to be mr square omega divided by I plus mr square. तो एग्जैक्टली देखो वैसा ही रिजल्ट आया है. I of the person into omega upon I of the person plus I of the platform. So what used to be mass of that person divided by mass of the person plus mass of platform multiplied by the relative velocity. Exactly वही होता था ना. Exactly वही form तो है. There is no change at all. Clear? Any problem? क्या नेगेटिव आएगा? नेगेटिव कैसे आएगा? नेगेटिव क्यों आएगा? क्यों नेगेटिव आएगा? इसको इधर ले जाओ. Is that clear? Any problem? गोली नहीं मारा है. गोली मार दी भी देगा तो भी क्वेश्चन बन जाएगा. चलो गोली मार देते हैं इसको. ओके. हाँ क्या? ओके जो भी जिसको गोली मारना है मार दो जिसको. So basically what I meant was the previous situation, but a ball of mass m prime and velocity v. Velocity v is tangential to this radius. ठीक है. Velocity v is tangential. दिख रहा है. So a ball of mass m prime and velocity v is thrown towards that person and that person catches it. And उसके बाद क्या होगा? उसके बाद all the three rotate together. The question is मतलब it is told to you that all the three rotate together. The question is find the final angular velocity. बहुत easy है. Find the final angular velocity. हाँ पॉइंट मास है. पॉइंट मास है. पॉइंट मास है एंड so even if it is a bullet which gets embedded, problem वही रहेगा. Yeah, please. M dash m plus m. तो डायमेंशनली करेक्ट नहीं है. हड़बड़ा क्यों रहा है? आराम से कर. हम्म, m डैश आर स्क्वायर वी, ठीक है। नहीं, m डैश आर स्क्वायर वी क्यों होगा? v स्पीड है, v इज द वेलोसिटी। पूरा क्यों काट दिया? हाँ, एक मिनट एक मिनट, m प्राइम v बाय, हम्म, ऊपर r छूट गया, m प्राइम वी आर। एम वी, एम या एम प्राइम, एम प्राइम वी आर, हाँ ये सही है। हम लोग क्या कंजर्व कर रहे हैं? लीनियर एंगुलर मोमेंटम। क्यों नहीं होगा? क्यों नहीं होगा बॉल का इनिशियल एंगुलर मोमेंटम? और नहीं पकड़ेगा तो नहीं होगा एंगुलर मोमेंटम। वो लीनियर मूव कर रहा है तो वो तो लीनियर ही मूव करेगा। नहीं, आर क्रॉस एम वी, हाउ इज एंगुलर मोमेंटम डिफाइंड? आर क्रॉस एम वी, तो आर क्रॉस एम वी किया तो कौन करेगा? बट सर क्या हाँ, नॉर्मली क्वेश्चन है ये, अब नॉर्मल क्वेश्चन नहीं है। हाँ, तो वहां तो हम लोग लीनियर मोमेंटम कंजर्व कर रहे होते हैं ना। एक बात समझो, अ पार्टिकल विच इज मूविंग लीनियरली, कैन इट हैव एंगुलर मोमेंटम? नहीं। तो नया नया थियरी ला रहा है, किधर से लाता है सब थियरी? अंदर का पार्टिकल्स एक ही पार्टिकल है। अ पार्टिकल मूविंग लीनियरली, कैन इट हैव एंगुलर मोमेंटम और नॉट? हाँ कि ना? होना चाहिए। क्यों होना चाहिए? क्यों होना चाहिए? क्वेश्चन का आंसर है इसलिए। देखो, ठीक है कोई बात नहीं, समझो अच्छे से समझो। इज दिस पार्टिकल मूविंग लीनियरली? ठीक है, सिंगल पार्टिकल, कोई रोटेशन रोटेशन कुछ नहीं हो रहा है। इज दिस पार्टिकल मूविंग लीनियरली? हाउ इज एंगुलर मोमेंटम डिफाइंड? आर क्रॉस एम वी। Does this have an angular momentum? It has an angular momentum. Clear? So an object which is moving linearly can have an angular momentum, because angular momentum is defined as the moment of the linear momentum. Okay, so if it has a linear momentum, obviously it is moving linearly, it has a linear momentum. But if you can find the moment of this linear momentum and that is not zero, then it will have an angular momentum. ठीक है, फोर्स जो एक्ट करता है, फोर्स एक्ट्स लीनियरली ना। फोर्स कैसे एक्ट करता है? सो व्हेन यू आर अप्लाइंग, सो दिस इज द ऑब्जेक्ट, आई एम अप्लाइंग अ फोर्स, तो ये फोर्स कैसे एक्ट कर रहा है? द फोर्स इज लीनियर. फोर्स तो इधर हो कैसे सकता है? फोर्स इज अ वेक्टर क्वांटिटी, तो एक स्ट्रेट लाइन में ही एक्ट करेगा ना. ठीक है, सो फोर्स इज लीनियर, बट इसका मोमेंट है कि नहीं है? इट इज गिविंग इट अ टर्निंग इफेक्ट. Similarly, so this object is moving linearly, but it can have an angular momentum. Clear? For a point object, so a point object moving linearly can have an angular momentum. Clear? तो अब बताओ इसका angular momentum होगा कि नहीं होगा? होगा. ठीक है, और होगा चाहे नहीं होगा. क्वेश्चन में एंगुलर मोमेंटम कंजर्व करना, लीनियर मोमेंटम थोड़ी ना कंजर्व कर देंगे. कैन वी कंजर्व द लीनियर मोमेंटम? यहां पे व्हाई कांट वी कंजर्व द लीनियर मोमेंटम? सोच के बोल. Right now in this question he is catching the ball which is moving with some speed. Can we conserve the linear momentum? Pure rotation को गोली मार, नहीं सीखे pure rotation. Is it, will the linear momentum be conserved? Why not? मूव ही नहीं कर रहा मतलब? वो कैच कर रहा है, कैच करके गोल घूमने लगेगा. लीनियर मोमेंटम कंजर्व हो रहा है कि नहीं हो रहा है? व्हाई नॉट? वही तो क्वेश्चन है. एक्सटर्नल फोर्स कहाँ है? एक्सटर्नल फोर्स वो कैसे एक्सटर्नल फोर्स है? मेरा सिस्टम है एम एम प्राइम आई, सब मेरा सिस्टम है. सो वेयर इज द एक्सटर्नल फोर्स? वेयर इज द एक्सटर्नल फोर्स? कहाँ है? नहीं है, तो कंजर्व कर सकते हैं लीनियर मोमेंटम. अरे सिस्टम क्या है मेरा? सिस्टम इज एम एम प्राइम आई, एवरीथिंग इज द सिस्टम. सिस्टम में सब है, तीनों ऑब्जेक्ट इज इन द सिस्टम. कैन वी कंजर्व लीनियर मोमेंटम? व्हाई वी कैन नॉट? एंगुलर एक्सेलरेशन को गोली मारना. आई एम टॉकिंग अबाउट लीनियर मोमेंटम, तो उसमें एंगुलर एक्सेलरेशन कहां से आया? हाँ तो अरे एक्सटर्नल फोर्स किधर है? ग्रेविटेशनल फोर्स, ग्रेविटेशनल फोर्स तो वर्टिकली लग रहा है. कैन वी कंजर्व द लीनियर मोमेंटम इन दिस डायरेक्शन? व्हाई नॉट? यस बोलेगा तो भी वाई पूछेंगे, नो बोलेगा तो भी वाई पूछेंगे. वो मेरा पूछना काम है. तो किसका? हम बॉल का मोमेंटम कंजर्व कर रहे हैं, हम पूरे सिस्टम का मोमेंटम कंजर्वेशन की बात कर रहे हैं. विल द लीनियर मोमेंटम बी कंजर्व्ड? यस नो? यस नो एक्सटर्नल फोर्स. यस हाँ मतलब भाई यस कॉमा नो एक्सटर्नल फोर्स. तो क्यों नहीं वो चीज अप्लाई किया यहां पे? फिर तो सिंपल हो जाता. नया चैप्टर है तो अब ये सोच रहा है कि अगर लीनियर मोमेंटम ही कंजर्व करना होता तो पिछले चैप्टर में ही आता ना, इस चैप्टर में क्यों आता? लिसन अप. इसका क्या, ये जो एक्सिस है अबाउट विच इट इज रोटेटिंग, वो उस पे फोर्स लगाएगा कि नहीं लगाएगा? थिंक यू आर ऑन अ मेरी गो राउंड. ठीक है, यू आर ऑन अ मेरी गो राउंड, वहां पे तुम खड़े हो. ठीक है, someone throws a ball at you, you receive that ball, you'll start rotating. But as you receive the ball, वो this platform, this should have moved like this. अगर ये hinge, अगर ये axis नहीं होता, this would have been a frictionless disc. तो ये क्या होता? ये disc should have moved like this. Is it moving like that? No. Why? Who stopped it? The axis. The external force तो है ना? हाँ? ओ कंफ्यूज, मिक्स मत कर कॉन्सेप्ट्स को. ठीक है, सो डू यू गेट दिस? तो यहां लीनियर मोमेंटम इज नॉट गेटिंग कंजर्व्ड. वापस एक बार, अगर ये मान लो कि ये एक्सिस नहीं होता, इट वाज जस्ट अ डिस्क ऑन अ फ्रिक्शनलेस सरफेस, इसको मिला इंपल्स, तो ये क्या होगा? ये पीछे जाएगा और ये क्या लगाएगा? इसके ऊपर, इस डिस्क के ऊपर फ्रिक्शन लगाएगा, तो द डिस्क वुड हैव स्टार्टेड मूविंग. राइट, द डिस्क वुड हैव स्टार्टेड मूविंग. हाँ बिल्कुल सही बोल रहा है. अब वो हटा दे, वो एक्सिस हटा दे, क्या हुआ? मूव करने लगा ना. राइट, सो इफ दिस एक्सिस वुड हैव नॉट बीन देयर, इट वाज फ्री टू मूव, तो क्या होता? दिस डिस्क वुड हैव मूव्ड. इज इट मूविंग? No. Why is it not moving? Because there is an axis over here. There is, what do you call it? There is an axle over here. Right. So that is stopping it. Matlab that axle or that axis is applying a force on this, and that is an external force. So linear momentum conserve nahi hoga. Correct. Is that clear to everyone? Angular momentum conserve होगा कि नहीं होगा? Angular momentum conserve होगा, लेकिन किस point के about? About this axis. Listen very carefully. If I asked you to calculate the angular momentum about this point, about this point, about this point, could we conserve the angular momentum about these points? Why not? Because the hinge force or the axis ka force is like this. Let's say it's like this. The force of the axis is like this. So this will have a torque about this point. This will have a torque about this point. This will have a torque about this point. Correct. But does it have a torque about this point? It does not. That is why we are able to conserve angular momentum, but not about any point. About which point? About this point only. आई बात समझ में? So the linear momentum is not conserved and the angular momentum is only conserved about which point? About this point. Is that clear to everyone? Any problem? अब कोई confusion है? Angular, linear, alpha, beta, gamma. Alright. Okay, now how do we solve this question? Now you tell me, this object is moving, this ball is moving linearly. Does it have angular momentum? It has. How much? M ठीक है. So extend the line of the momentum and drop a perpendicular. So momentum into the perpendicular distance. So what is the initial angular momentum? The initial angular momentum is mv prime r. Okay. Finally everything is moving together. Matlab all these three things would have an angular velocity of omega. So we can write the combined moment of inertia multiplied by omega. Okay. So what is the combined moment of inertia? I plus mr square plus m prime r square. That's the combined moment of inertia of the system multiplied by omega. Bring this down. Done. Clear? नहीं हम मानेंगे नहीं. एक क्वेश्चन और बनाओ तब मानेंगे. एक क्वेश्चन और बना के, एक क्वेश्चन तो खुद से बनाना पड़ेगा तभी मानेंगे कि समझ में आया है. ठीक है. इज दिस क्लियर टू एवरीवन? सीधा तुम लोग को नहीं समझ में आता ना, तुम लोग उल्टा समझ में आता है. तो कैच कर रहा था तो नहीं समझ में आ रहा है तो फेंक देते हैं तो शायद समझ में आ जाए. सुन. So man, mass m, holding a ball, mass m prime, standing on the periphery of a platform which has a moment of inertia I, radius r. This entire thing is rotating already with an angular velocity of omega. Already rotating with an angular velocity of omega. ठीक है. Now he throws that ball with a velocity v. ध्यान से सुनो. Throws that ball with a velocity v tangentially with respect to the platform. ठीक. Throws the ball with a velocity v tangentially with respect to the platform. ठीक. Find the final angular velocity of the platform. Find the final angular velocity of the platform. And the man does not move with respect to the platform. This is given to you. The man does not move with respect to the platform. Find the final angular velocity. Find the final angular velocity. हम्म, क्या डाउट है बोल। पूरा कहानी सुन लिया, अब तेरे को नहीं नहीं समझ में आई ये क्या है। सोच, कुछ नहीं बोलेगा। सोच क्या है। तो तू डिपेंड करेगा ना, तू कौन सा डायरेक्शन पॉजिटिव ले रहा है। तू डायमेंशन की ऐसी की तैसी क्यों कर देता है। ओमेगा माइनस वी आर लिखा है, ये क्या है। ओमेगा वी बाई आर होता है ना, तो ओमेगा माइनस वी आर क्यों लिखा है। वी बाई आर लिखेगा ना। तो कौन सा डायरेक्शन पॉजिटिव लिया है तू। एंटी क्लॉकवाइज पॉजिटिव लिया है। अगेन एम ओमेगा तो तू लिख दिया, आर किधर गया। उसका बॉल का एंगुलर मोमेंटम में एम इंटू ओमेगा माइनस वी बाई आर लिख दिया, वो बात सही है, बट फिर आर कहाँ गया। आर छूट गया। हाँ तो उसको ओमेगा वी बाई आर कर और इंटू आर कर, बाकी ठीक है। किस साइड को पॉजिटिव लिया है।
ये वाला।
तो ये माइनस होगा ना।
हाँ मतलब
मतलब नहीं, गड़बड़ हो जाएगा फिर। ये नेगेटिव होगा,
ये फिर प्लस हो
तो दिस इज पॉजिटिव।
नेगेटिव।
नहीं, दिस v इज विद रिस्पेक्ट टू द प्लेटफॉर्म, फिर ग्राउंड के रिस्पेक्ट में v रहेगा क्या। बोल ना। v माइनस ओमेगा आर हो जाएगा। हाँ फिर ठीक है। देखने से ये मेरे को नहीं समझ में आया ये. अच्छा. नहीं, what you're trying to write is, I understand what you're trying to write, but प्रॉब्लम क्या हो रहा है ना, तू गलत क्वांटिटी लिख दे रहा है. ठीक है, सोच. वी हैव टू राइट द एंगुलर मोमेंटम. ठीक है, एंगुलर मोमेंटम ऑफ व्हाट, ऑफ दैट बॉल. ठीक है, so to write the angular momentum of the ball, what are you using? Are you using I into omega or are you using mvr? mvr use कर रहा है. ठीक है, so m is m prime. What will be the velocity with respect to ground? v minus omega prime. v minus, चलो assuming that the final velocity is omega prime, and तू पॉजिटिव किसको लिया है, एंटी क्लॉकवाइज को तू पॉजिटिव लिया है. फिर हाँ, ओमेगा आर प्राइम माइनस वी, सो दैट इज m into v, then you have to multiply it with r, mvr. समझा? तो m into ओमेगा r minus v into r. आई बात समझ में? Okay, so which direction you want to take positive? एंटी क्लॉकवाइज को पॉजिटिव लेना है. ठीक है, ले लिया. I am assuming that the final velocity of the platform is anti-clockwise omega prime. That's what I am assuming. I am free to assume whatever I want. ठीक है? So I am assuming the final angular velocity of the platform will be omega prime anti-clockwise. ठीक है? Now let's write the angular momentum conservation equation. What is the initial angular momentum? What is the initial angular momentum? Everything is rotating with an angular velocity of omega. So I plus mr square plus m prime r square multiplied by omega. That is the initial angular momentum. Equals, what is the final angular momentum of the ball? Final angular momentum देखो, you can calculate it in two ways. या तो I omega लगाओ या फिर mvr लगाओ. That's it. ठीक है. If you want to find it using mvr, so you have to find the velocity with respect to ground. ठीक है. Okay, this velocity is with respect to the platform. What is the velocity of this point of the platform with respect to ground? That is omega prime multiplied by r. ठीक है. When I am saying v is the with respect to platform, it is with respect to which velocity of the platform? Final velocity. If nothing is given, this is with respect to the final velocity of the platform. Correct? Okay. So what is the velocity of this point of the platform? It's omega prime into r. हाँ, final वाला. Omega prime into r. Do you get that? ठीक है. So the velocity of this ball with respect to ground would be omega prime r positive minus v. Do you get that? ठीक है. ओमेगा प्राइम r is in the left direction, मतलब this is positive, this will be positive, क्योंकि एंटी क्लॉकवाइज डायरेक्शन you have chosen as positive. Is that correct? So this omega prime r is positive, this v will be negative. ठीक है. So what do I write? I am going to write m prime, and then what is the velocity with respect to ground? The velocity with respect to ground is omega prime r minus v multiplied by r, mvr. Is that clear to everyone? Otherwise what can I write? Otherwise what can I write? I can write इसका moment of inertia क्या होगा? m prime into r square, that is the moment of inertia, multiplied by what should I write? Omega. Moment of inertia multiplied by omega. Now I want to find the omega with respect to what? With respect to ground. तो अगर इसका velocity is v with respect to the platform, its angular velocity with respect to the platform would be v by r. Is that correct? So the final angular velocity, or the angular velocity of the ball with respect to the ground, would be the angular velocity of the ball with respect to the platform plus the angular velocity of the platform. क्यों अलग आएगा? क्यों अलग आएगा? But I am telling you, choose one thing. Know what you are doing. यहाँ पे हम लोग लगाए हैं mvr, यहाँ पे लगाए हैं I into omega. So whatever it is, find it accordingly. Obviously you will get the same answer. Angular momentum तुम्हारे calculate करने से change थोड़ी हो जाएगा. जो है वो है. Okay, so this is it. So the final angular momentum would be m prime into omega prime r minus v multiplied by r. ठीक है? And then plus I plus mr square multiplied by omega prime. That is the final angular momentum of the platform plus the man. ठीक? Is that clear? अब यहाँ से whatever omega prime comes out to be, that will be your answer. हाँ. R तो कहाँ चेंज हो रहा है? We are conserving angular momentum just before catching and after catching. Just before catching, after catching. ठीक है? That's how we are doing it. Just before catching, after catching. और यहाँ पे क्या है? Just before releasing and just after releasing. तो वो practically वहीं पे रहेगा. ठीक है? Alright, so then we meet in the next class.